Alrighty, folks. Hello and welcome to Math 3108. This is Abstract Algebra 2, or you could think of this as an introduction to groups, rings, and fields, and of course their applications. Now, my name is Gary Basdell. I will be your instructor for this term. Today's lesson, what we're going to be diving into is arithmetic in the integers. Now, algebra was born out of arithmetic, so this seems like a good place to begin. So for this lecture, this lesson, the next lesson afterwards, what we're really going to be building upon is the foundations of everything. So we're not specifically talking about groups, rings, or fields right now, but we're building up to all the important skills that we're going to need to be able to handle those. So let's jump into the material, but before we do that, let's just make sure that we're all on the same page with the notation that we're going to be using throughout this course. So let me jump over to my whiteboard here. All right, some notation. So the integers will represent by z. So this is the set of integers. So that's everything from negative infinity off to positive infinity, but whole numbers. So 3 dots there. Think of that -3, -2, -1, 0, 1, 2, 3, and again, all the way up to positive infinity from there. So no decimals whatsoever. Now, variations of this, we can have z, and in the superscript, a greater than or equal to 0, which would indicate all of the integers from 0 all the way up to positive infinity. So the set of integers, again, starting at 0, building from there, and all the way up to positive infinity. We'll also have z in that superscript plus. So this is dealing with positive integers. And remember, 0 doesn't count as a positive integer, so this is starting at 1, 2, and again, all the way up to positive infinity. We're going to have the rationals. So the set of rational numbers. So this is everything of the form a over b, where a and b are in, so that's the symbol for in the integers, but b cannot be 0, obviously, because we can't divide by 0. Problematic. Our set of real numbers. And the 2, we're not going to see these specifically in this class. We'll be using them in the next lesson. So this is z mod nz. So this is the set of integers, or ints, mod n. And if you don't know what that means, don't worry. We will define this more formally next lesson. And we also have z mod nz with an x on the top, and this is the set of units, which again, we'll define units when we get to that, but just again, remembering the notation at this point. So the set of units mod n. All right, so that's the basic notation that we are going to be using for the rest of the term, so thus introduced now. So let's jump into the slides. So in terms about talking about the arithmetic inside of Z, what we want to be able to first start with is what's known as the well-ordering axiom. So the well-ordering axiom is a property of the positive integers, but not just the positive integers, but the integers starting at 0, again, going all the way up to positive infinity, so no negative numbers in there. And the axiom states that every non-empty set S, so S is a non-empty subset of this Z starting at 0 going all the way up to positive infinity, of all non-negative integers, contains a least element. And by least, I mean the smallest element overall. So there is some integer a inside of this set S such that a is less than or equal to b for all the b's inside of S. So basically what we're saying is there's going to exist a smallest element in there, which is going to be less than or equal to every single other element inside of that set. All right, so let's see examples of this. And going back to my board here, let's move this up. So this is dealing with the well ordering. So Z greater than or equal to 0. So again, all the integers starting at 0 going all the way up to positive infinity. Let's take a set S. And this set is, I'm just going to grab some random integers. So let's take 100, 36, 4, 17, and 1000. There we go. Then clearly we can see here that one of these numbers is in fact smaller than everything else. In that case, this is 4. Because we have 4 is strictly less than 100, 4 is strictly less than 36, 4 is equal to 4, 4 is less than 17, and 4 is less than 1000. So this would be the smallest element inside the entire set. So that's our first example here. Our second example, just something to note, the natural numbers, n, which I did not define this, but this is the set of all positive integers. This is the same thing as Z superscript plus. So this is starting at 1, 2, 3, all the way up to positive infinity. It doesn't contain 0. So if I union this, or if I add to it the element 0, what we end up with is Z greater than or equal to 0, which we already know we can grab any subset inside of here, and based upon that well-ordering principle, this works out. But let's change this a bit. Let's take n, the natural numbers, and we're going to add to it, so the union of that with -1 and 0. So this is the set, now starting at -1, 0, 1, 2, all the way up to positive infinity. And we could ask the question, does this also work? Now, it's not Z starting at 0 all the way up to positive infinities, but this still does have a smallest element inside of here. These are all still integers, and we know it stops at -1. So every single subset of this would in fact hold true. So this also works. Let's do one more change of this, and then we're going to look at things that don't work and why they don't work. So I'm going to union with this. We'll do -3, -2, -1. But I'm not adding 0 into this. So this is the set starting at -3, -2, -1, skipping 0, 1, 2, all the way up to positive infinity. So we're missing a number. Is that okay? Yeah, no problem, because this still does have a smallest element inside of there. It's -3 in this case. So every single subset that I'm going to have of this is in fact going to have a smallest element. All right, so let's look at a couple of examples where it's not going to work. So not well ordered. And again, let's just bring this up a bit. So we'll look at two examples here. So the first example is going to be the real numbers. So why is the real numbers problematic? Well, it's problematic for this reason. Let's pick a subset S out of this. So S is going to be equal to the open set between 0 and 2. So it contains everything in between 0 and 2. It just doesn't include 0 and it doesn't include 2. So what's the problem with this? Well, there is no smallest element. And how do we see this? Well, easily. We can just pick an element inside of here. So this is in between 0 and 2, so let's take a half. So if I start at a half, let's get smaller than this. Let's divide by 2. So if I divide by 2, well, then I'm at 1/4. Can I divide by 2 again? Of course I can. So now I'm going to go to 1/8. And I keep going, 1/16, 1/32, and you get the idea from here. We can keep going and going and going. And as long as we have an infinite amount of decimal places, we're never going to end up with the smallest number because we can always get smaller and smaller and smaller. So this doesn't work for specifically this reason here. This is a set that doesn't have a smallest element. All right, well, what about 2? Let's start with the integers. So all integers in this case. So this is starting off from negative infinity going all the way up to positive infinity. Now we saw in the examples above that having negative numbers in there wasn't technically a problem as long as there was a smallest element. So let's now grab a set S, and this set S is going to contain negative infinity all the way up to 0. So the open set again, so it's not going to contain negative infinity because obviously it can't, and it's not going to contain 0. It doesn't really matter if it did contain 0, but the same idea still holds. So in this case, this subset of Z doesn't have a smallest element because negative infinity is not an element. It constantly gets smaller and smaller and smaller, or more and more negative. So this doesn't work. So this is in fact a non-empty set. Or I should say subset to be correct, with no smallest element. There we go. All right, so that's the well-ordering principle. We've seen examples now of where this works, where this doesn't work. What's an application that we get from this? Well, let's go back to my whiteboard, or my slides here. So what we get from this is the division algorithm. So the division algorithm is, let's let a and b be integers, and the only condition on a and b is that b has to be strictly greater than 0. So it can't be 0, has to be greater than 0. Then there exists a unique integer q in R such that we can decompose a as a product and a sum. So we can take the product of a b times q plus r, and where r is going to be bounded. So r can be greater than or equal to 0, but it has to be strictly less than b. So there's 4 variables here. Each variable has a specific name. So a is the dividend, b is the divisor, q is the quotient, and r is the remainder. Now, the division algorithm is something that we've been doing, even if it wasn't formally defined back in the day. This is something that we've been doing since grade school. Let's see an example of what I mean by that. Bring all of this up. So in grade school, we were asked to do something along the lines of, let's say, what is 82 divided by 7 without using a calculator? Well, the only way we can do this was with long division. Now, that's probably something you haven't seen in quite some time. Very useful skill to remember to have. But let's go through an example of this. So long division, I get 7 into 82. How do we do this? Well, the first thing I do is I ask, well, how many times does 7 go into 8? Well, it goes once. Now, 1 times 7 is 7. I'm going to do a subtraction here. So 8 minus 7 gives me a 1. I bring down the 2. And now I ask the question. So every time I go through this process, I ask the question, what's the relationship between 7 and 12? And more specifically, what I'm asking is, which one is larger? If the number on the bottom here, this 12 right now, is larger than whatever I'm trying to divide by, I repeat the experiment again, or I repeat this loop again. So since it is greater than 7, I ask, well, how many times does 7 go into 12? It goes once. So I add another 1 up here. 1 times 7 is 7. I do a subtraction. 12 minus 7 gives me a 5. Do I stop? Well, again, I have to compare this to what I'm dividing by. Since this time around 5 is less than 7, I stop. So since 5 is strictly less than 7, we stop. And what do we get from this? Well, we get that this 5 is the remainder. $82 is the dividend. 11 is our quotient. And 7 is the divisor. And again, we're making the claim that when we did this, that I could now break 82 down into a multiplication and a summation. where I'm going to take the quotient and the divisor, multiply them together, add the remainder to that, and I should get the dividend. So if I check this, 11 times 7, well, that's going to get me 77. Now I do the addition, so 77 plus 5, well, that gets me 82. So yeah, 82 can be decomposed into this 11 times 7 plus a remainder of 5. That's the division algorithm. Like I said, we've been doing this since grade school, but we might not have formally defined it at this point in time. In the next part of the video series for this lesson here, we're going to actually prove the division algorithm. So we'll see you at that point.